Welcome to the IRENA online seminar series. So, welcome you all to this exciting talk. It's my pleasure to introduce our guest speaker for today's seminar, Dr. Vinicius Placco. Dr. Placco has degrees of BSc, MSc, and PhD from the Universidade de São Paulo in Brazil. He has also worked as a postdoctoral fellow at both Universidade de São Paulo and the National Optical Astronomy Observatory in Arizona, USA. With a passion for exploring the mysteries of the universe, Dr. Placco served as a science fellow at Gemini Observatory in Hawaii and as a research assistant professor at the University of Notre Dame in Indiana, USA. Currently, Dr. Placco is the associate astronomer and the head of the US National Gemini Office at the NSF's Neuer Lab in Arizona. He is renowned for his contributions to galactic archaeology and is a core member of the R-Process Alliance, making him a very prominent figure in the field of astronomy and astrophysics. We are privileged to have Dr. Vinicius Placco as our speaker today, and we look forward to his enlightening presentation. Please welcome him. And Dr. Placco, I think the stage is all yours.
Thank you, Averjit. Can you hear me?
Yeah, I can hear you.
Okay, good. Well, I really appreciate the kind words. I really don't know about prominent, but I do what I can to contribute to IRENA, to JINA. Thank you very much for the invitation. I'm really happy to be here. One thing I should say is that I think my involvement with JINA started almost 20 years ago now, when I was an undergraduate in Brazil working with experimental nuclear physics. So now I think I'm speaking almost 20 years later from the other end of the stick, right? So I'm really happy to be here. And should I start?
Yeah, it's a pleasure to have you for this series.
Yeah, thank you very much. Yeah, and
so the talk
okay,
is 45 minutes, and I will give you a 5-minute warning at the 40-minute mark.
Okay.
And how do you want, like, should we the audience ask questions in the talk, or should we ask them to ask questions at the end of your presentation?
Whatever people are comfortable with. If people want to interrupt me, that's fine. I really don't mind. So whatever people feel comfortable with.
Okay, sure.
Yeah, all right. Well, okay. So thank you very much for having me. The title of this talk is, well, Neutron Capture in the Wild, Finding Our Process-Enhanced Metal Poor Stars in the Milky Way and Beyond. The beyond here is a little bit of a provocation. I think it's, when we talk about beyond the Milky Way, it's mostly beyond in time, not in space, right? We still cannot go into really faraway galaxies and find our process-enhanced stars in situ there, but we can go beyond in terms of time, right? So I think my goal here is to focus really on the observational part and how do we find these stars, right? I think this is IRENA focus area 2, right? Stellar abundances. And I think what I really want, the points that I want to drive here is how do we, observational astronomers, really find the stars that we use to get our process elements and then feed that to our friends in all other areas of JINA that can give us an idea about what's happening in the atmosphere of those stars. All right, so the subtitle for my talk, just because it's an observational talk, is, and let's see if I can move slides. Yes, I can. It's going on a fishing expedition, right? Because sometimes I see part of my job as a fishing expedition, just because you have this huge sea of stars in the galaxy, in the universe, and you're really trying to find which ones are the really interesting one, right? And so just so you have an idea, so when you look at a stellar field like this one, imagine that this is kind of a 1 square, well, this is 1 degree across, which is really the width of your finger, right? So it's a very tiny field, and you have thousands of stars in there. So how do you really find a star that's interesting enough in terms of our process enhancement, right? So the summary of my talk is really, how do you go from this, and how do you point to 1 star, and then you get a very detailed chemical abundances for that particular star. So the whole story here for this talk is, how do we go from that to the actual abundances, and how do we contribute to JINA and IRENA's kind of a broader goals, right? And as many of my physics professors would tell me, everything starts with a physics question, right? Or with some sort of a curiosity about what you're trying to accomplish with some sort of a research. And in my case, one thing that always fascinated me is the spectrum of the sun. This is what you see. This is a very, very, very high resolution spectrum of the sun. You know, the bottom is about 4,000 angstroms and the top is about 8,000 angstroms. So you see here thousands and thousands of spectral lines, right? And once you have all of those spectral lines, you can measure their position, you can use your atomic physics to identify, you know, which elements are those. You can use the width to identify how much of those elements are there. And then you can start building up your knowledge about the sun, for example. And then we should do that for other stars. So then my physics question is, so how do we go from a universe that had nothing, right, hydrogen and helium, all the way to what we see here in the surface of our sun? So when we are talking about, you know, the theoretical knowledge or the theoretical base for all of this, I think we all know and love this article, right, from 1957. I think this is really the base for a lot of the things we do. Of course, in the 66 years that passed after this was published, we accomplished a lot, right? And some of those things I want to show you today, but this is really the foundation, right? And unfortunately, all of those authors are no longer with us. I think Margaret passed 2020. And also, well, yeah, so then this is kind of the contribution. So that's kind of a theoretical basis. So when we talk about these heavy elements in the universe, well, how do you make them? It's really, you know, through stellar evolution, right? That there's really no way around it. You have stars with different masses. They evolve in different time scales, different internal temperatures, different internal furnaces that will form an array of different elements depending on your mass. And then you can form those elements either by the burning stages or the explosive stages of stellar evolution. And once those are formed, they enrich the interstellar medium, and then the next generation forms, and so on and so forth. So we have this constant recycle of elements being formed and forming new stars. And from point A, Big Bang, to point B today, a lot has happened in terms of stellar evolution, and that's why we see the universe the way we see today, right? And if we look at the periodic table at your redshift 0, right, today, this is what we believe the elements came from, most of them, right? So we have here some fractions and some coding here for from Big Bang nucleosynthesis all the way to emerging neutron stars, exploding white dwarfs. So we have an idea about where all of those elements come from. And some of the challenges for the observers is, so how do we go from this knowledge and how do we find those elements in situ, right? So we want to observe them in nature, right? That's our laboratory. So we want to observe them in nature and try to tell a convincing story about how the universe and our galaxy should have evolved so we would have the chemical composition that the sun has today, right? So the main question here becomes, how do you go from this, right, hydrogen and helium, all the way to this, which is the solar atmospheric abundances as of, well, 8 minutes ago, last time I checked, right? So this is what we have in the surface of the sun, right? We have everything, almost everything from hydrogen all the way to uranium. So all of those elements are there, we measure them, and what we want to do now is just measure those elements in other stars and try to come up with a story about how those elements are there and how they are there in those quantities. So we could try a very simple thought exercise here, which is, if you imagine that the sun, or the surface composition of the sun, is just a sequence of stellar evolution events that produced a given amount of elements, mixed together, the next generation was born, evolved, mixed together, and so on, we could come up with some sort of a chemical time machine with a very simplified model, right? And this is what you will have, for example, right? So you start from 0, and then each generation, if we make the very basic and not so correct assumption that each generation would contribute with the same amount, then n generations later, you would go from having nothing to having the sun, right? However, if you want to disentangle the chemical composition of the sun in terms of individual contributors, that's really kind of impossible, right? Because you had the universe had 9 billion years to evolve chemically until the sun was born. So we don't know how many generations could have evolved, how many stars would have exploded in order for the sun to have the chemical composition that it has. So what's the next best thing? So if you look at this plot here, as simple as it is, this model, what if we look at those stars in here, right? If we could in principle find or pinpoint what is the second generation or the third generation, maybe then we could talk a little bit about the second and the first, right? So then we can turn back the clock, but we need to be really far back in time, right? If we try to do that with the sun, then it doesn't work. So I think all of this is to show that my interest is really here. First, second, third generation in terms of this chemical clock of the universe. So then how do we find those? I think that's one of the main questions here. So we have this, field of study that has been really kind of growing over the past few decades, what we call, near field cosmology. To me, it's called the next best thing, right? Or galactic archaeology or stellar archaeology. And what we are trying to do here is really have this toy model of the universe. And I don't know if you can see my mouse. Okay, good. Yeah, so then you go from an universe with hydrogen and helium. You have your first massive stars, mostly massive stars. Then you would form some of the elements. Then the typical mass of the gas clouds that would form stars would decrease, and then you would form lower mass stars. And somewhere in here, you would have your first R process event, for example, your first astrophysical event that would give you R process. And this is what is showing here on the right-hand side. This is from a very nice, I think it's a book chapter from Anna and Alex. It's in the archive now, so I think this is a really nice picture. And it's talking about dwarf galaxy archaeology and stellar archaeology. But in principle, what you're trying to do is find stars here in this regime, right? Where you can still pinpoint how many or how did the progenitors look like. So that's what we are mostly trying to do. So then throughout this presentation, I want to answer 5 questions or 4 questions, and then I have some sort of a proposition, right? So it's when and how were these R process enhanced metal poor stars were formed? How do they look like? Where do you find them? And how do we find more? And then to answer that last question, I have the curious case of this particular star that we found recently, and we are hoping to get this out to the public soon. All right, so I'll go through the first 3 questions very briefly. I'll spend a little bit more time in the 4th, which is really what I'm interested in doing. And then the 5th, just talking about this particular star. So when, how were these R process enhanced metal poor stars first formed? So we have a few different culprits for this, a few different scenarios that people argued that are suitable for that. We have neutron star mergers, and one evidence was this gravitational wave event from 2017. People try to fit, and you see here on the left-hand side just spectra at different times taken after the event. So people try to fit models, red dynamical models, lanthanide-rich or blue lanthanide-poor models, and see if they fit the actual data. People did that with some success, right? And what you can take away from this is, if you feed a certain model, you could, in principle, if you look at, for example, on this panel here, the luminosity as a function of time, you, in principle, could tell how much of our process elements you formed on that given event, right? There's some fits here on late stages, and then when you go to the early stages of the explosion, then there's not a good fit for this particular amount. But then this is progress, right? And this is telling us that there's something there that we really need to investigate. And we need more of those events to happen, of course. And we haven't had any, at this magnitude ever since. So this is one potential kind of a progenitor for these really early R process events. We also have collapsars. It's a very nice figure here from the Siegel 2019, comparing neutron star mergers and collapsars. I think the main difference here, at least in broad terms, is the neutron star mergers would be more frequent. The rate would be about 10 times the rate of collapsars. However, collapsars would yield more R process in terms of mass on a given event, right? So then the balance between those two could potentially explain, and you see here on the bottom, the europium abundance distribution as a function of metallicity, right? So if you have different contributions from these two progenitors, in principle, you could try to fit what we see happening in the galaxy, for example. All right, so this, and there's a third one here, which I just chose not to talk about, but it's worth mentioning, is the common envelope jet supernova. So there's this tree, and I can provide references later for people if they're interested in. So this is the culprit, right? And then we have the culprit and the evidence, and I won't go through these tables. I just left them here for completeness because these are kind of a very nice summary tables about, well, I want to talk about the main R process, right? And these are, the conditions that the R process requires, the main R process forming, from barium all the way to uranium, mostly in, say, neutron star mergers, the tidal ejecta and the dynamical ejecta. And here on the right-hand side is just some sort of a summary of the evidence of the different R process sites. And we'll talk about this in a moment, about this universal pattern for the second and third peak and the rates, right? Because we have large scatters in europium abundances as we go towards lower metallicities, and these stars are, well, really hard to find. So kind of this is I really suggest that people go through these very nice reviews to learn a little bit more. All right, so how do these stars look like, right? So then you have that big field of stars. So how do they look like in terms of spectral features, and what are we looking for? Now, I decided to put a historical slide here just for fun, just because I've been looking at this, and I called this exercise mindful procrastination, just because, I had to do something and I wasn't feeling like doing that. So I decided to just do a deep dive in the literature for europium references. And one that I found that was really, to me, was really fascinating is from Lunt, 1907. And on the presence of europium in stars, right? I think this is, again, I won't read through all of this. I just highlighted some interesting takes here. So europium was indicated as a disturbing element. I think europium observations were made in 1905 during a solar eclipse in the surface of the sun. And then this person here confirmed the presence of europium in a star other than the sun. And then it's a very interesting take here that it says that, well, if europium is there, it's likely that the other elements that are europium-like would also be there, right? So it's already, 100 and almost 120 years later, we're still arguing about some of those things. But then I think this is all really well established that we can see europium in many, many, many different stars, right? And then, 2013 here, that was the first kind of evidence of a line list that I found, which I found it was super, super interesting that we still measure all of these lines. 4129 for the observers is very popular, 4205, 4435, with the contamination of calcium. And the story goes on, right? And then, 1970s, I think you have one of the first europium as a function of metallicity plots showing, hey, this is what's happening with the europium as a function of metallicity as we go back in time. And measurements, in 73 and 85 of really chemical abundance patterns of stars, which is really our goal. That's what we want to do, right? And this here is just to give you all an idea about how far we've come, from 1907, really looking at europium in stars all the way to today, and the amazing things we're all doing, right? Okay, so the R process signatures. So how do we find them? Find europium, right? Europium, it's a good representative of the R process. There are many strong, in relative terms, absorption lines in the optical wavelength regime, so they're fairly straightforward to measure, in high resolution on the given temperature regime. So that's what we're looking for. So if you want to find those metal R process enhanced metal poor stars, you have to find metal poor stars, but with lots of heavy metals, right? Which sounds kind of a counterintuitive, but that's what we have, right? We use this iron over hydrogen notation here, where the sun is our 0 point. So metallicity, this is the iron over hydrogen. So anything with metallicity is below 0 is a metal poor star, and we are interested in it. And as you go from 0 to -1, -2, -3, as you see here on this top panel, all the way to -7, you just see all of your lines disappear, right? For our process work, we don't want to go to -7 because then you wouldn't have even our process to begin with, right? You want to find where is your sweet spot where the low metallicity and our process enhancement really start happening together. And what we look for in terms of spectral signatures depends on the resolution. If you look on this panel here with all the blue colors, the metallicity increases as you go down, and these are calcium lines, so you can see the effect the metallicity has on calcium lines. So calcium lines are a good indicator in medium resolution of low metallicity stars, right? So then if you go try to find stars with really narrow calcium lines for a given temperature regime, of course, then you can find out which ones are the metal poor ones, and then you would study them in higher resolution, and that's what you see on the right-hand side. You would find all sorts of interesting R process enhanced lines. And you see here, the europium here is super, super evident, right? This is a really strong 4129 line. And then you also have another one here that's 3819, huge europium line. And then you can find all sorts of interesting R process elements as well. And you see that that line is really so strong that it's really stronger or kind of equivalent to an iron line, right? So then you're decreasing your metallicity, and then you're finding this really R process enhanced stars. On the left-hand side, we just have some definitions. I wouldn't be too tied to those. I think it's kind of a more empirical definitions, just so we know what we are doing and dividing stars in groups. But this is what we're looking for. Low metallicity, lots of R process, right? Low metallicity we can see in lower resolution spectroscopy. R process we cannot. So then, you know, that's why it becomes difficult. And this is how a low metallicity star, R process enhanced, looks like in terms of the high resolution spectrum, right? This is HD 222925, well known to many people in this audience. I see Ian is here, so you know, we know of this star as a very bright star with lots and lots and lots of R process elements. It is metal poor. The metallicity is -1.3, meaning it's about maybe 25 times less iron over hydrogen than the sun. So you don't see a lot of those metallic lines for light elements, right? You know, not a lot of iron lines, but when you look at the blue side of the spectrum here, you see lots and lots of R process lines. So then the goal is just measure those lines and get the abundances, right? And this spectrum here, I think it's from the NUID spectrograph. Here on Keat Peak, but just for completeness, but I think this is not the spectrum that actually gave the data I'm showing in the next slide. And then if you have a star like this is kind of the amazing work that you can do when you find a really bright star and it lots and lots of our process elements. You can observe that star with our big optical telescopes, and you can go to space with Hubble Space Telescope, and you can find lots and lots of interesting lines. See, this is 2200 angstroms, right? So this is really blue. This is really far in the UV, only accessible through space. But then you can measure, for example, tungsten, right? For the nuclear physics experimentalists, you know, in the audience, you know, tungsten, right? I think you use tungsten in your beam, you know, beam stops, you know, when you're doing your radioactive beam. So, well, you can find that in HD 222925. But in the end, these two works here, they were, from Ian, they were able to measure, he was able to measure 1,300 lines, if I counted this correctly, all across the spectrum, the UV and the optical, and detecting 63 metals, right? So this kind of becomes a new standard to study metal poor stars enhanced in our process. And you see how many elements we have, right? 63 plus hydrogen, helium, and I think we have 7 upper limits, if I'm counting this correctly. And then you have this beautiful, beautiful abundance pattern here with all of these elements. And you can tell things about the universality of the R process, for example, right? The second and the third peak fit really well. The first peak, not so much. So you can talk about the R process being universal here, and maybe there's other processes happening on this lower side. All right, so this is what we can do. This is kind of our gold standard now. Well, gold, we also measure gold for that matter, right? So this is the standard that we want to go for, right? Finding more of these, right? Which is hard because not only they're rare, this one is super bright. So then you can do space-based observations for this as well. All right, so we know how they look like. So where do we find them? Well, if you look up and if you look at the Milky Way galaxy, you can actually find our process-enhanced metal poor stars pretty much everywhere, right? And this slide here is busy on purpose, right? That's really on purpose because I just wanted to show that we have identified our process-enhanced metal poor stars in the Milky Way halo, in the disk, in the bulge, in all of those ultra-faint dwarf galaxies, stellar streams, classical dwarfs. So it's everywhere, right? And you can see that all of these studies, you look at the europium scale here, you have many, many stars above 1. And this is europium over iron above 1. This is 10 times the solar value, right? For these low metallicity stars, we are reaching, metallicities of -3, which is in that scale 1,000 times less iron over hydrogen in the sun, right? So this is really pristine metal, super enriched with our process. And there's a lot of work being done now in ultra-faint dwarf galaxies, for example, right? These kind of a self-contained systems, I think you have a very good laboratory there to do those studies. So we find many of those, even though it's hard to find, we find many of those. And one of some sort of the efforts that a few of us, myself included, and I think Ian is here from the R Process Alliance, we established this collaboration some years ago with the goal of just really finding more of these, right? At first, just do lots and lots of observations and trying to find more of those really are process enhanced metal poor stars, and then trying to understand why they are the way they are, the fractions of those stars on a given astrophysical environment, and then do some sort of collaborations with modelers and other people. And this is what we've been trying to do since maybe early 2017. So we've been working a lot. We see here, you can see that we have a logo and we have a website. So that really makes us legitimate, right? So it's a legitimate collaboration with a logo, a website, and lots of published papers, right? So we have been working hard and there's a lot of interesting things coming. And based on what we know from these stars, well, europium greater than 0.7, see, from 1994 to 2021, the community combined found 100 of those, if I counted things right in the histogram. And we in the RPA, within 4 years, we found 72. So we got really good at finding those, even though they're rare and the fractions are still lower than we would like. We were able to really bump those numbers up, and we hope to continue doing that. And here on the bottom left is just showing you some of the successes that we had over the years, right? So this is where do we find the stars and what we are doing to find more. So then that's the question. So how do we find more of those? And the question here becomes, how do you effectively choose targets? Because, well, if I had an infinite amount of time at a given telescope, I would say, hey, just observe everything, right? Just get me a high resolution spectrum of every star in the sky, and then we would know, right? We would have good statistics. But that really doesn't work with time allocation committees and telescopes for some reason. So you cannot really ask for everything. You have to have a very good justification for what you want to observe. Looking at a field like this, you say, well, how do I find the ones that are potentially are process enhanced? And some sort of the analogy I like to do sometimes is, well, people say that an image is worth 1,000 words, right? This here on the left-hand side is M31 or Andromeda Galaxy, very beautiful image. And on the right-hand side, you have 1,000 words just for completeness. So in my mind, if this image is worth 1,000 words, a spectrum is worth n images, where n is how much detail you want from that particular star, right? Because if you think about it, a spectrum is really a collection of images on very, very narrow wavelength regimes, right? So then you put all of those together, you have your spectrum. So then where do you find the balance of the right n to get, for example, low metallicity stars, and then you have your R process. So how do you go from images to high resolution spectra? So where is your happy medium? And this here is just showing, this is a really high resolution spectrum, right, of a star that is enriched in carbon and in our process elements. And what I'm going to do here is decrease the resolution of this star as a function of just decreasing the resolution, as you can see here. And then we have to establish where do we stop in terms of how do we know if the star is metal poor, for example, right? Or how do we know if the star is R process enhanced? So essentially what I'm doing is I'm just integrating over pixels and increasing my signal, right? So it's faster to observe that star, but then I have less details. And if you see that if you go from a really high resolution to a really low resolution, which is really photometry here, you can still see a bump here due to the calcium lines, to their metallicity, and the carbon. So in principle, you could even see the carbon here. So then what you have to do is decide where do you draw your line when you're observing or when you're doing your spectroscopic follow-up. So if you have really high resolution, you can go from hydrogen to uranium, and you can do all sorts of very interesting things as I showed already. If you go to this moderate resolution, 10 times lower than this, you can see here calcium lines, hydrogen lines, carbon band. In principle, if you squint really hard, there's the barium line is somewhere in here, the 4554 barium line, which is really strong in this particular star. You could see it here, but then it's not very reliable because you really need high barium to see the line. So then you're really biasing your samples if you're doing this. If you decrease the resolution even further, then what remains is your low metallicity proxy, right? And carbon and maybe magnesium, right? And calcium, of course, because it's our metallicity proxy. So the idea is, well, can we use those really low resolution data or narrowband photometry, which are really cheap in terms of the time you invest to observe a given field? Can we use those tools to pre-select stars? And then as we pre-select them, we are increasing our chances to find those R process enhanced metal poor stars. And the answer is yes, right? So then is, how about we observe everything? So what if you have, for a field like this, if you have information for each point source here, right, imaging, but then if you do imaging correctly with the correct filters, then you can increase your chances of finding interesting stars. And this is what these two surveys are doing. There's more surveys. I think the reason I'm mentioning these two is because these are the ones I'm using now to find the stars that we're finding. And these are really tiny, small 0.8 meter telescopes, fully robotic. They just keep observing the sky every night and just really sweeping the southern hemisphere, the northern hemisphere, with a 2-degree squared field of view and, well, a big footprint in the sky. And what's nice about those two projects is that they have 12 filters, right? You see here on the top, there's 7 narrow band filters, right? Really narrow. And on the bottom, 5 broadband filters. So they have 12 filters. And what you do, you have information for all of those. For every pixel of every image, you have those 12 pieces of information, which is your kind of a third dimension, which is your spectral information. So what you do is, what's interesting about this, though, is that it does have filters centered in very interesting filters for stellar work. For example, let's just focus on this calcium K here, right? It's very narrow. So what the filter is doing is essentially integrating the light on that particular wavelength regime and giving you a number, right? So then as you change your metallicity, the flux in that filter will change, right? So what you're doing here, you're replacing your spectrum with points. And then what we do is what we call a spectral energy distribution, which is another way to say a really, really low resolution spectrum. And we know that towards the blue, since we have many metal lines, then those filters in the blue, the flux in the blue, should really react to changes in metallicity. And this is what we see here. On the left-hand side, I hope you can see the thing moving here. So these are spectra with different metallicities from 0, I think, all the way to -4, -1 to -4. So as you can see, as the metallicity decreases, the line strength decreases and the overall integrated flux increases. So here on the bottom, you see that if you hold your temperature still, if you have a good handle on your temperature, then you have filters that don't change much, but then your metallicity sensitivity is here, right? And this is what you see here on the right-hand side. These are real stars from these two surveys. And what you see is if you have stars with spectroscopic values, right, on a narrow temperature regime, you can assume with a lot of confidence that a lot of the changes in the flux in the blue side are due to changes in the metal content of those stars. So if you want to find low metallicity stars, and if you look at these guys over here, if you want to choose which one are you going to follow up with high resolution to get more abundances, you would choose the one on the top, right? Because then it has more flux, meaning that the lines are weaker. So chances are this is a low metallicity star. And then once you observe many of those, you would hope to find the R process enhancement in there as well, which is a tricky thing to do, right? So then you have all of those out of those 12 filters, and we know that they tell a lot of the physics of the star, right? They don't tell you everything, but they give you a pretty good handle. For example, the temperature. Well, we have been doing photometric temperatures for decades now, right? We know this. This is really kind of a basic physics on black body radiation. So if you do a combination of two of those narrowband filters, you can get a pretty good handle on the temperature. And if you get smart about doing combinations of colors, including those blue filters that I showed before, in principle, you can find regions in color space where your low metallicity stars live, which is great, right? Imagine that you have 1 million stars, and if you put those stars in a plot like this, well, if I keep observing stars over here, chances are that most of those would be low metallicity, right? So then that's the ones we want. And this is exactly what we've been doing to get low metallicity stars. And then, well, you may be thinking that, well, this really calls for machine learning, right? And we've tried to do something like that as well, using neural networks, artificial neural networks, using all of those color combinations, right? So you have 12 magnitudes. So if you do color combinations, right, one filter minus the other, you actually have 60 combinations of those. So if you have spectroscopically confirmed temperatures and metallicities and carbon abundances, for example, and you have the photometry, you can just throw that into the machine learning algorithm, and it would give you a value. And then you can apply this to all of the unknown stars and then find new ones, right? We did this with relative success. For temperatures, you see that's really nice because, we know how to do this. For metallicities, we have some success down to -3. Depending on the data sets that you use, training sets are really important for machine learning, for example. And we could even get carbon abundances. We cannot get any R process enhancements here, but if we use our domain knowledge in the sense that, well, if I want to find an R process enhanced star, a metal poor one, it has to be, well, metal poor on a certain temperature regime, and, most likely, or I would prefer if it was low carbon abundance, because then the metal lines wouldn't be buried in the carbon bands. So, right, so you can do things like that. You can pre-select interesting stars. And then you can do also all sorts of crazy things, because nowadays we have Gaia, and everybody talks about Gaia these days. So what you can do is you can get Gaia parameters for all of those. You can integrate the orbits, and you can start placing those stars within, for example, major merger events that the Milky Way had in its history. For example, there's some examples here in the top: Sequoia, the Gaia sausage, Enceladus. So you can move stars around in those energy angular momentum spaces or in terms of dynamics, and see if you can add the chemistry and the dynamics and tell a convincing story about the history of those stars. So you can do all of that, right? And that's how you find more of them, right? So you're essentially trying to increase your odds. And that's why I said, fishing expedition, right? So, but then you have to know the river that you're fishing in, right? So you have to know exactly what to do, and you have to increase your chances of finding more of them. And now, with the minutes I have left, I'll just talk about the curious case of this particular star. That was really, I wish I could tell you that it was really an intentional search, that I really found this because I really aimed for it, but it was really by accident, right? Because we were looking for low metallicity stars in general, not only R process enhanced, but this one turns out to be R process enhanced within this sample of stars that we observed. All right, so this is the power in numbers, right? So you go from these really large narrowband photometric surveys, so you have 20 million stars in there, and then you go to your medium resolution step if you want to. You observe hundreds of stars, for example. That's what we did. Hundreds of stars were observed, and then within those hundreds of stars, you find a couple of them that you really want to have more detailed studies. And then you go to, well, in this case, same telescope, different instrument, and you get really detailed abundances for those. So then this is just the story of these two stars, for example, right? So what we did to find this particular one, 1424, was we looked at a color space, and we found the region in that color space where the chances of finding low metallicity stars would be higher. And in this case would be this region over here, right? In this two color space using those particular filters. And what we did is we observed around 500 stars in this place here, hoping that most of them would be metal poor. And what it turns out that most of them are metal poor. And if you look at here, this is showing the same data set just with some sort of different constraints as a function of metallicity. And you can see that, well, regardless of the metric that you use, usually more than 90% of them or more are metallicity below -1. And 80 are metallicity below -2. So we're really finding a lot of them just by using this very naive color diagram, right? And once you have all of those, you decide, well, I want to observe two of them. And this is what you see here on the left-hand side. So this star over here, that's J1424, 2542, right? So that's the one we observed with this high-resolution spectrograph at the Gemini Observatory called GHOST. We previously had a medium resolution spectrum. That's what you see here, right? Even though this star is really enriched in europium, you cannot see any evidence here just because the resolution is too low. But from the calcium lines, you see that it's low metallicity and low carbon abundance. So then you follow that up in high resolution, and then this is what you find, right? You find all of the interesting lines, europium, dysprosium, strontium, all of the fun stuff, right? So then you have all of these lines for you to measure. And then for this particular star, we measured 308 absorption features for 36 different elements from carbon all the way to thorium. And these are some of the examples, just so you have an idea about the data from this new spectrograph. This is the carbon G band. The little squares here are the actual data. And all of the lines and the shaded areas these are just synthetic spectra, some sort of realizations of a star with the same atmospheric parameters as the observed star and varying the abundances of carbon in this case here and europium here on the bottom. This is the infamous 4435 line that has, a calcium component here. But then you can measure europium, and you can go, like some of the other stars, you can measure lots and lots of interesting elements. You can measure thorium. There's 3 thorium lines here. And I'll just, let you, look at this for a couple seconds and just to have an idea that we can really measure all of those lines. And we would never be able to see those lines in lower resolution, right? These are really small. And if you look at normalized flux here, these are really tiny, right? And this is what you have. So you measure all of those elements, and then you can try to combine the abundances and compare them with theoretical models and try to come up with an explanation about how this star was formed. How was the progenitor population? So what we did, we look at the light elements first, from carbon all the way to zinc, and we compared. So the measurements for the star are all the circles here, right? And you see the lines here are different so these are the yields from population 3 faint supernova, the yields from the star fit code from Alex Hager. So you see here, we had 10,000 realizations of this particular star, and we just fit all of those with the models. And on the overwhelming majority of the cases, the abundances fit very well a low, kind of a quote unquote low mass faint population 3 supernova, right? So we can say, for example, if you just look at the light elements, they fit a progenitor population with 13 solar masses that exploded right after the Big Bang. So that's where the light elements come from, right? On this very simplistic model. When you look at the heavy elements, then as I showed you, you can measure lots and lots of different elements, and you can compare with the R and S scaled solar system abundances. And you see that for the R process, which is the blue line here, the second peak fits fairly well as we anticipated. The first peak has its issues, not issues, it's just a different process happening. And we do have a very kind of enhanced thorium here, which we also know this is kind of an actinide-boost phenomenon that some stars have. So it fits the solar system pattern to some degree, right? And then, well, if you know the right people, if you have the right colleagues, you can tell them, hey, can you run your models for me on these abundances and see what happens? And that's what we've done. You know, Erica Hombach, I don't think she's here, but she's also known from many of you here in JINA and IRENA. She ran one of her neutron star merger models with a given equation of state in trying to minimize mostly the ratios between the first, the second, and the third peak, right? So then you see here that zirconium, europium, and thorium fit very well. So those are the constraints of the model. And we wanted to see if everything else would fall within the same constraints of those models. So we end up with a neutron star merger with these two masses here, 1.66, 1.27, and that's the best fit we found, which is still off for some elements, right? We know that some measurements have to improve, but we also know that the models have to improve. So this is always a back and forth. So it's not anybody's fault or anybody is there to blame. It's just we really need to continue improving on both sides, having more abundances, having better models, and trying to do those connect and make those connections, right? So in principle, for this particular object here, the proposition would be, well, you had one progenitor population that generated those light element abundances. You would have this neutron star merger that generated the heavy elements, and those two events happened at some point, and the yields from those two elements mixed together. And I know that may be a stretch, but then there would be the base for the formation of this star here, this J1424, right? So that would be more or less what we believed happened for this particular object. And since it's a bright-ish star, we can go a little bit further, right? We can get the Gaia data that I talked about from the Gaia space mission, and we can integrate the orbits for the star. We can look at the kinematics, the dynamics, and really place this star in the galaxy today and 10 billion years ago, right? We can also determine with some uncertainty the age and the mass of this star, and this is doing isochron matching. We are not doing the thorium over europium ages just because it's an actinide boost. So then those particular age indicators wouldn't work, and we don't have uranium for this one, unfortunately. But then doing isochron matching, even if this is more qualitative results in a sense, the star is old-ish, 10 billion years old, plus or minus 3, which is, I know is a lot, but again, it's an old star, it's an old population. The star is low mass, 0.8 solar masses, which fits our understanding of evolving really, really slowly. And when you look at those energy angular momentum diagrams, and when you look at the position of the star in terms of the maximum height above the plane of the galaxy and eccentricity, in this particular case, we cannot put this star in any known structure or any known chemically tagged group in the galaxy yet, right? I'm sure that at some point we can find other stars. And this is what you can do, right? So, and again, this is one star. And this is how things, in this field, sometimes they go a little bit slow. And with the RPA, we are trying to make this go a little bit faster. Is as we find more and more of those, we can start talking about fractions of occurrence of given events, right? And then we can do kinematics, and we can start really placing those stars where we think they were born. Of course, assuming some sort of assuming that we know the history of our galaxy, right? Which is another big if, but we have some handle on those things. So the last thing I want to say, and I actually came into my last slide before my 5-minute warning, right, Abhijit?
You have about 2 minutes from now.
Oh, 2 minutes. Great. See, that was completely planned. Yeah, I had no idea. Thank you. All right. So this is really the what now, right? Well, when we talk about these R-process metal poor stars, I really wanted to convey how important they are, but at the same time, how difficult it is to find them, right? And when you come across a star like the one I showed, which again, I have to admit it was by accident, right? It was a really happy accident. But again, an accident with a purpose, because we knew that we were observing low metallicity stars. So then we could find one of them. It's just not a very common occurrence. So for this particular star, we're proposing this kind of a two progenitor scenario. And we know that if instead of having one of them now, and we have 100 and some R2 stars, if we have 1,000 or 500, it helps us decrease our error bars when we're doing chemical evolution analysis, for example. And moving forward, I think my three takeaways is, well, statistics, right? We need to find more, and we need to have homogeneous samples and analysis. And this is something we have been working on. And it's a lot of work within the RPA. And to our modeler friends, talk to your observer friends, right? Really tell us what you need, how you need it, things that would constrain better your models. And then we can try to go for those particular constraints within the observations. Yeah, and I just put this plot here just because I find it amusing that we've been doing this for so long, and so far we only have about 30 stars with europium and thorium measured, low metallicity stars, right? Which is a low number if you think about the history of the field, right? But we're still working on this, again, difficult measurements. And I'll leave you with a very nice picture of a laser in a telescope. Here's my email and contact information. I'm happy to share the slides or, yep, well, thank you for your time, I guess, and I'll be happy to take any questions.